Hello everyone, this is Abhishek Datta, your new physics faculty, and today we are just going to start a chapter that is of gravitation. Okay, this is one of the most important chapter of your syllabus, and it is having some of the important concepts as well. So the first concept of this chapter that is of Kepler's laws of planetary motion. This chapter was also included in your class 9, I think, right? So here some of the concepts will be revised and you will got to know some new concepts as well. Now, what are the Kepler's laws? The Kepler's laws are divided in three segments. That is Kepler's first law, second law, and third law. The Kepler's first law is also known as the law of orbits. Now, what I mean by law of orbits, so in this case, we know that every planet is rotating about the sun in an elliptical orbit, right? So let's draw that. So there is an elliptical orbit and there is a planet who is rotating in this direction, okay, with respect to the sun. And in this case, this is the sun who is located at any of the focus of this elliptical orbit. So Kepler said in his first law that all the planets move around the sun in elliptical orbit, having the sun at any one of the focus of the orbit. So as you know that the ellipse is having two focus, so the sun can be kept in any of the focus and the planets are rotating with respect to that of sun. Okay. Now this was the first law. What is about the second law? The second law is also known as law of areas. Now what I mean by law of areas, now if you just join the planet and the sun with a line, then in that case you are just able to understand that each time the planet is rotating with respect to that of sun, so it is covering some amount of area, right? If you just join them, that means the planet and the sun with a line, that means the planet is revolving around the sun and it is covering some of the areas. So in the second law, it was told that a line joining any planet and the sun sweeps out equal areas in equal interval of time. This is the area velocity of the planet remains the constant because we know velocity equals to displacement upon time. So in this case, as the planet is revolving around the sun, so it sweeps out equal areas in equal interval of times. Suppose the planet sometimes is at this position. Now, if you just draw the lines with respect to that of sun also, so whatever the area you are just getting over there and whatever the area you are just got from the previous position, the both of the areas will be equal with respect to the time period. That means how much time has been elapsed between these two positions, the time will be given to you and the areas of these two positions that will be equal. This is the second law of Kepler. That is the line joining to any of the planet with that of sun sweeps out equal areas in equal interval of time. So you can say the area velocity is constant. Now the third one, that is the law of periods. Now what is about the law of periods? So in that case, whenever the planet is rotating about that of sun, so obviously it is taking some time. And the line joining the sun and the planet, it is actually the radius. It is denoted by r. So he said that if you just square the time period, that means whatever the time is taken by the planet to complete one revolution, if you just square the time period and if you just make a cube of the radius in this case, then the t square is directly proportional with that of r cube. That means the ratio you can find out the t square by r cube ratio that is equals to constant. Okay, it was said in Kepler's third law that is also known as law of periods. So therefore, I'm just repeating that concept again that the square of the period of revolution, that means every planet takes some time to complete one revolution, right, around the sun. So if you just square the time period, then it is directly proportional with that of cube of its mean distance from the sun. So we can say that the ratio of t square by r cube will be constant. Now the derivation of these laws are not required. I'm not writing down the statements because the statements are already available in your book and you can get that from here. Okay. Now we are just moving to the famous law, that is of universal law of gravitation. Now what is about the universal law of gravitation? It was actually proposed by Newton. Suppose we are just talking about the two of the masses. One is having the mass of capital M, another is having the mass of small m. They are separated by some distance that is equals to r. Now what we know, that if two of the objects are separated by some distance, then every object will try to attract another one with some force. That force is known as a force of gravitation. So this object which is having the mass of capital M will try to attract the smaller one, right, with some force in this direction. And the smaller one also will try to attract the bigger one with some force in this direction. So what is the magnitude of the force? It is denoted as F, and it is directly proportional to the product of masses, and it is inversely proportional to the square of the distance between them. So we can conclude that the force of attraction between any two materials, that is directly proportional to their product of masses, and they are inversely proportional to the square of the distance between them. So if we just conclude, that means if we just write down, that is F is directly proportional with that of capital M small m divided by of r square. So when you will just break the proportionality, a constant will be introduced, that is of G capital M small m divided by of r square. Here G is known as a gravitational constant. Okay, G is known as gravitational constant. It is having the value of 6.67 into 10 to the power minus 11 Newton meter square by of kg square. Remember that one. This is your childhood definition. That means whatever the expression you already know from your class 9. Now, whatever the question that me asks to you, that write down the law of gravitation in vector form, right? In vector form, whenever you are told to write down, then how to write that? So we'll explain in the next slide. Everything will be same, but there the vector notification will be used. So in this case, for the ease of your understanding, we are assuming that one of the mass that is of m1 and another mass that is of m2. They are separated by a distance of r. So obviously they will try to attract each other by some force, that is the force of gravitation, right? So in this case, the m2 will apply a force on m1, right? So in this case, that force will be written in vector form. So it can be written as f of 1 2 vector, right? It can be written as f of 1 2 vector. Now m1 will also apply some force on m2, and that can be written as f of 2 1 vector. So remember one thing, f of 1 2 is what? That means force applied on m1 due to m2. What is f of 2 1 vector? That is a force, applied on m2 due to m1. Now here we will also consider some of the unit vectors. That means there will be the unit vector that will be pointing the mass m2 in this direction, and it can be written as r of 1 2 cap. And there will be another unit vector that will point towards the mass m1, and it can be written as r of 2 1 cap. Okay, so what we know according to our universal law of gravitation, that is of, we can write down that f of 1 2 vector. F of 1 2 vector means this is the force applied on the mass m1 due to the mass m2, right? This is equals to how much? This is equals to g into m1 m2 divided by of r square, right? but here you have to show the direction, in which direction the force is being applied. So who is applying the force? Mass m2 is applying the force on the mass m1. So which unit vector I should write down? This unit vector I should write down, which is pointing towards the m1. So in this case, r21 cap will be included over here. Now, f of 1 2 vector is equals to, we are having a value that is of g into g into m1 into m2 divided by of r square, and here we have just included a unit vector that is of r of 21. R of 21, it is a unit vector that is pointing the direction, that means in which direction the force is being applied. You are applying the force on the mass m1, right? So m2 is applying some force on the mass m1, so we have written the force as f of 1 2 vector. It is equals to gm1 m2 by r square multiplied by the unit vector that is pointing towards the m1 mass. So in this case, if you just see the direction of this f of 1 2 vector and this r of 2 1 vector, they both are opposite in nature, na? So that's why you should include a minus sign over here, right? Because r of 2 1 cap is in the opposite direction of f of 1 2 vector. Similarly, if you just write down f of 2 1 vector, that is equals to the same expression we should write down. F of 2 1 means what? That means m1 is applying some force on m2. So it is having the magnitude of g m1 m2 by of r square multiplied by the unit vector. So who is applying the force? M1 is applying the force on m2. So I should write down this unit vector that is of r of 1 2 cap. Okay, and in this case, if you just see that r of 1 2 cap is showing the direction in this way, right? But f of 2 1 vector is in the opposite direction of r of 1 2. So in this case also I should include a minus sign over here. So I am repeating the concept again. F of 1 2 vector, this is the force applied on mass m1 by the mass m2. It is having the value of gm1 m2 by r square multiplied by, you have to remember who is applying force. Mass m2 is applying force on the mass m1. So which vector we should use? This r of 2 1 vector we should use, right? So f of 1 2 vector, it is equals to minus of gm1 m2 by of r square multiplied by r of 2 1 cap. This r of 2 1 cap and this f of 1 2 vector, they are opposite in nature, so that's why we have used a minus sign. Similarly, we have used the next expression, that is of f of 2 1 vector and this r of 1 2 cap. They are just directly opposite to each other, so that's why we have used a minus sign over here. So if you just compare these two equations, this is the equation 1 and this is the equation 2, so you can write down that f of 1 2 vector, it is equals to minus of f of 2 1 vector, right? From these two equations, even we can write down that r of 2 1 vector, sorry, you can write down that r of 2 1 cap, it is equals to minus of r of 1 2 cap, because they are directly opposite to each other. You just see on the diagram, r of 1 2 cap and r of 2 1 cap, they are just directly opposite to each other. That's why we can represent it in this way. Similarly, f of 1 2 vector and f of 2 1 vector, they are also directly opposite to each other, so that's why you can write it down in this way, right? Now we are proceeding to find out the dimensional formula of your gravitational constant g, because some of the questions are also asked from this concept. Now to determine that, what we know from our Newton's law of gravitation, that is of F equals to g into m1 m2 by of r square, or someone can use the expression that is g into capital M small m divided by of r square. Any of the formula you can use, okay, but you have to define that one whenever you are writing that, because the examiner doesn't know what the m1, what is the m2. So you have to define that m1 is the mass of one of the object, m2 is the mass of another object. Okay, now I want to find out the dimensional formula of g. So g is equals to f into r square divided by m1 m2, right? F is having the dimensional formula of mlt to the power of minus 2. R square is having the dimensional formula as L square. M1, M2 is having the dimensional formula of M square because they both are mass. So what's the final dimensional formula we are getting? That is of m to the power minus 1 LQ t to the power of minus 2. This is the dimensional formula for G. Now we will understand what is the force of gravity. Now what do you mean by force of gravity? Now every object in our Earth's surface is attracted towards the surface of our Earth. Suppose this is the surface of our Earth and there is an object is being placed which is having a mass of m. So obviously the object will be attracted towards the center of our Earth by some force. So that force is known as the weight of the object. What do you mean by weight of the object? It is defined as W. It is actually one type of force by which the object is attracted towards the center of Earth. It is having a magnitude of mass into gravitational acceleration, right? So we can relate the two of the forces because the weight is a one type of force. So we can write down that F is equals to mass into gravitational acceleration. But from Newton's law of gravitation, we are just able to know that F is equals to G into capital M small m divided by of R square. Now why I'm just writing down this expression? Now if we just consider for this case, now capital M is the mass of Earth. Capital M is the mass of Earth. R is the radius of Earth. And what is M? M is the object which is being placed on Earth's surface, right? So I'm just redrawing that one. Suppose this is the Earth's surface, this is the center, this portion is the radius, right? So the mass of our Earth, that is of m. So there the object is being placed which is having a mass of m. So what is the separated distance between the object and the center of our Earth? The separated distance is r. So that's why I have just written r square. Our Earth is having a mass of capital M and the object is having a mass of small m. So that's why I've just found that expression that force equals to G into capital M small m divided by of R square. Now these two forces are having equal value, right? Both of these two forces are having equal value. So we can say that M into G is equals to G into capital M small m divided by of R square. So this m will get cancelled out and we are getting G equals to G into capital M divided by of R square. Now the mass of our Earth, that is of 6 into 10 to the power of 24 kg, and the radius of our Earth, that is of 6400 kilometer, or you can say that is of 6.4 into 10 to the power of 6 meter. These values I am just giving you because you can use them in solving the numerical questions. Okay. Now we are just going to write down the mass of our Earth in a different way. Okay. If we just write down, let's see what's the value we are just getting. Suppose what you know that mass is equals to what? We know the basic formula that mass equals to volume multiplied by of density, right? So what is the volume for a sphere? That is equals to 4/3 pi r cube, right? That r I have used because the radius of our Earth we have assumed here. So if I just assume that our Earth is a one type of sphere, for that the volume should be 4/3 pi r cube and the density that should be of rho. So for m we can write down this one, right? That is a 4/3 pi r cube multiplied by of rho. So what will be the value of g? G was having the value of G into capital M by of R square, right? So if I substitute that value in that expression, what I will get, that is of G by R square, that will remain same, multiplied by 4/3 pi R cube multiplied by of rho. So this R square will get cancelled out with that of R cube, right? So we are getting 4/3 pi r rho multiplied by of G. So this is the relation between the gravitational acceleration and the gravitational constant, or you can say this is the relation between gravitational acceleration and the density of our Earth. Okay. Now the next topic, that is what is the variation of the value of this g, small g, when you are just moving up from our earth surface. Okay, that means I just want to tell you that this is our earth. We are assuming this is the center of our earth, so obviously this is the radius of our earth. So you just want to calculate that if an object is placed at this height, suppose there is an object which is having a mass of m. Okay, so in this case, obviously the object is in the gravitational field of our earth. Our earth should have a specific area of its gravitational field, and the object is in the gravitational field of our earth. Okay, so at this point I just want to calculate the value of the g, small g. How the value will be changed, I just want to see. Okay, so for that, what the expression we should use, that means we are assuming that the object is placed at a height of g, sorry, the object is placed at a height of h from our earth surface. We have to calculate the total distance from the center. So can you determine that what is the total distance from the center? What is the total distance from the center of that object? That is of r plus h now. So when the object was at earth surface, suppose we are assuming when the object was at earth surface, at this time the g was g into m by of r square, right? That means sometimes the object was at this point, so the separated distance between the object and the center of our earth, that is equals to r. So the gravitational acceleration is having the value of g into m by of r square, right? But when the object is placed at a particular height of h, then the gravitational acceleration will get changed, and it is equals to g dash, and it is having the value of g into m by of r plus h, that of whole square. So if I just get this is our equation number 1 and this is our equation number 2, then I should find out a relation between this g and g dash. So I should divide them. So I'm just dividing equation 1 and equation 2. So what I will get, that is of g upon g dash, it is equals to gm by of r square divided by gm by r plus h whole square. This gm get cancelled out now. So what I will get, that is of g upon g dash, it is equals to r plus h by of r, that whole square. One small step jump I have just done with a simple mathematical calculation. That's why. Okay. So if I just get modify this expression, what I will get, that is of, here we are getting g upon g dash, that is of r plus h by of r, that whole square, right? That expression I'm just getting. From this I can write down that g equals to g dash into, if I just divide it by parts, that means r by of r, that is of 1 plus of h by of r, that of whole square. So there is a relation between the g and the g dash. That means the gravitational field, gravitational acceleration when the object was placed at the earth's surface, and g dash is the gravitational acceleration when it was placed at a particular height from a earth's surface, right? Now it can also be changed now that g dash, it is equals to g by of 1 plus h by r, that of whole square, and I can write down it is equals to g into 1 plus h by r, now 1 by of that function, so we can write down that is of minus 2. Suppose 1 by of 2 square, it is equals to 2 to the power minus 2. 1 by of 3 square, that is of 3 to the power minus 2. So that's why I can write it down. So according to your binomial expansion, you can do what? You can just multiply the power over here. So you will get a final expression, that is of g into 1 minus of 2h by of r. Okay, so this is the final expression by which you can relate these two terms. Now we are going to find out that what will be the effect of depth when of that g actually. Okay, now what will be the effect of depth on that value of small g? Now suppose in the previous case what was done, the object was moved at a particular height. Now if I just do one thing, that this is the earth, okay, this is the center of our earth, so obviously this is the radius of our earth. So initially the object was placed at the earth's surface. It is having a mass of m, but after some time we have just placed that object at this point. Okay, so at a particular depth, if you just place that object, so we are just assuming that it is at a depth of h, right? It is at a depth of h from the earth's surface. So from the previous position, at position 1, if we just calculate the value of g, it is having the value of g into m by of r square. But at a depth of h, how to find out the value of g dash? In this case, obviously the radius will get changed, right? But the mass can be broken down in a different way. Now if we just write down the g as it is equals to 4/3 pi r rho multiplied by of g, it can also be written in this way, right? So whenever you are just moving in through the surface of a earth, so whenever you are just moving at a particular depth from a earth's surface, so obviously you should consider that density of a earth as well as the radius of a earth and the gravitational constant. So we'll prefer this formula. So if you just at a depth of h, so what is the distance of that object from the center? Just calculate the distance of the object from the center. If you just see carefully, now the distance between these two, that is of r minus of h. That means I'm just taking the distance of the object from the center. That the total distance was r, it has come to a depth of h, so the distance between them, that is of r minus h. So g is equals to 4/3 pi, that will be of, instead of writing r, it will be of r minus of h rho multiplied by of g. So this is what your equation number 1, this is equation number 2, and it will be your g dashed, right? So just get a ratio over there, that is of g upon g dash, that is equals to 4/3 pi r rho g divided by 4/3 pi r minus of h rho multiplied by of g. This 4/3 pi rho and this g get cancelled out, so we are getting r by of r minus of h, right? So if I just reverse both of the sides, what I will get, g dash upon g, it is of r minus h divided by of r. So if I just get a partial division over here, that means dividing by parts, I'm getting 1 minus of h by r. So g dash by g, it is equals to 1 minus h by r. That means g dash equals to g into 1 minus of h by r. That's all. This is the relation between the gravitational acceleration at a particular depth and the gravitational acceleration at Earth's surface. So this is the first day of our class. So just say that up to that point, whether everything is understandable or not, try to practice some of the numerical questions based on this application. Okay, so tomorrow we'll come with a new video of gravitational field, gravitational potential energy, escape velocity, orbital velocity, and so on. Thank you so much.